Yeah, so this was a merged paper. So both of the merged people are going to give a talk, or representatives from both groups. So yeah, so this talk is about efficient, robust, sparse estimation tasks in high dimensions. Before I can describe what these two things are, I kind of need to describe both of these things separately, because this talk kind of combines two separate orthogonal kind of aspects of high dimensional data analysis. And before I talk about them together, I should really introduce them separately. So first, let me talk about robust estimation tasks in high dimensions. And this is a phenomenon known as model specification, which is the very natural observation that we model a lot of things by like basic things like Gaussians or whatever, but data is never truly Gaussian. It's often close to, it's well modeled by, but it's never truly Gaussian. So as a simple example, suppose we have samples. Suppose we're modeling some phenomena by Gaussians with some unknown mean and covariance identity. Okay? In reality, we're never actually going to get samples from a true Gaussian. We're going to get some samples from some distribution which is close, say in TV distance to this Gaussian. So what if we get samples from some distribution with TV distance epsilon from one of these Gaussians? So this is morally equivalent to, but we need to like switch, that's the thing. Oh, sorry. So this is morally equivalent to, we get samples from one of these Gaussians, but then an epsilon fraction of these samples are corrupted adversarially. Okay? And the goal is, given these corrupted samples, can we recover, I guess in this case the only parameter here is mu, so can we recover mu? Okay, so here's the problem statement. I hope that this makes sense. So this is introduced by Huber in the 60s, and it was kind of a foundational question in the field of robust statistics. And what he showed is an estimator mu hat, which gets error, L2 error to mu, roughly O of epsilon. Okay, and this rate is optimal, it turns out. You can't do better. Unfortunately, his algorithm is very inefficient. It runs in extremely exponential time. And despite kind of how fundamental this problem was, it wasn't known how to do this efficiently until very recently, where myself and a lot of people and a concurrent work of Lybrov and Paula kind of at the same time created polynomial time estimators which got error O of epsilon root log 1 over epsilon, so almost optimal. And in follow-up work, we actually got O of epsilon. I'm lying a little bit. Lybrov and Paula got a slightly different rate, but it's not built on that. And we also got similar rates for other things such as covariance estimation and so forth. Okay, and again, this paper, we want to ask the question, how does robustness interact with other aspects of high-dimensional data analysis, specifically sparsity? So now let me context switch to introduce what I mean by sparsity. Hopefully this is a bit more well understood. Let me start with a very basic question, just an extremely basic question. Given epsilon greater than 0, how many samples from a d-dimensional Gaussian, with mean mu and covariance identity, do we need to estimate its mean? So this should be fairly standard. We need d over epsilon squared samples. And this is both sufficient and necessary. And you just do something like the empirical mean. Okay. So now the question in sparse estimation is, can we get away with fewer samples if we make sparsity assumptions? So suppose mu is k-sparse. How many samples do we need? Well, this is also kind of folklore that you only need k log d over epsilon squared samples. Or technically, log of d choose k or whatever. And this is achieved by some sort of truncated empirical mean. Okay. In other words, sparsity allows us to get away with sublinear in the dimension sample complexity. And the main question of this paper is, do the statistical gains, in these kind of sparse settings, can they persist when you have epsilon corrupted samples or whatever? And can we get these gains using efficient algorithms? So this is kind of the central question that we address. So now let me pass my...
Now I'll state our main results for sparse Gaussian mean estimation. So given an epsilon corrupted set of samples from Gaussian distribution with mu, mean mu and identity covariance, where mu is k-sparse. So there's an inefficient algorithm that has error in the order of O epsilon if the number of samples is order of k log d over epsilon squared. Also, we have an efficient algorithm that has error in the order of epsilon times log square root of log 1 or epsilon if number of samples is in the order of k square log d over epsilon square. I'll explain why there's in k square later. So we have similar results for sparse covariance estimation, linear regression, logistic models, and spec models. Also note that this k square log d or epsilon square is tight for any statistical query algorithm. Okay, so now let me state our main algorithm. So our main technique is to find a set of weights, W1 to Wn, to assign to each samples, and such that this truncated mean estimation is a good estimation of the true mean. So the problem reduces to how do we find the set of good weights. So we will use the convex programming algorithm framework in this previous paper, that is to construct a separation oracle and use ellipsoid algorithm. So the problem further reduces to how to construct a separation oracle for this problem. So we will use the top k sparse eigenvalue and eigenvector of the empirical covariance. So to be specific, this is our main observation. So let x1 to xn be an epsilon corrupted samples with number of samples is in the order of k log d over epsilon square. And let w1 to wn be the set of weights. So we consider these two quantities. The first one is our truncated mean estimation. The second one is the weighted empirical mean. So we show that if our estimation is bad, so we'll have this top k sparse eigenvalue of the empirical mean minus the identity is large as well. So we can compute this quantity, and to see if it is large, then we will need to adjust the weights. And if it's small, then we will just accept this weights and use that for our estimation. Also, if number of samples is in the order of k log d over epsilon square, we show exists such good weights that this quantity is small. Okay, so there's a problem, because if we want to compute the sparse eigenvector and eigenvalue, it may take exponential time. So a natural approach to use the convex relaxation of sparse PC. This is very standard. So this is the standard convex program for sparse PCA. So we have a very similar proposition, but note that here we will require number of samples in the order of k square log d over epsilon square, which is actually necessary for this sparse convex sparse PC convex relaxation. Okay, so we will use this convex program to construct our separation oracle. Okay, so that's pretty much our technique. I'll list some open problems. So we propose a polynomial time algorithm for sparse estimation problem, but the polynomial order is very high, so probably we can design some more practical algorithm, like the filtering approach in this paper. So can we design a conditional lower bound for using a reduction from plan-to-click or sparse PC when the number of samples is in the order of k log d over epsilon square. The last one is we have shown the robustness introduced some statistical versus computational trade-off, like the k versus k squared issue in our problem. Can we develop a more general theory for the robustness in this setting? Okay, that's pretty much it. Thank you.